Hi everyone, Sungjune and I will be presenting the haptic edge display for mobile tactile interaction. This work was done by Sungjune, Lawrence Kesler from Stanford, advised by Hiroshi Ishii from MIT Media Lab, and Sean Follmer from Stanford. So mobile devices we use now have gone through a tremendous breakthrough. It has transformed from just a phone to a multimedia device in which phone is just one of its applications. While millions of applications have been developed, the means of interaction has remained the same. It's mostly just touch on a screen. With this type of interaction, there are several issues that arise. First, while the screen is filled with rich variety of information, the haptic interaction is very limited. It's mostly just vibration. Second, most of the content and interaction relies heavily on the screen. Thus, in circumstances where the screen is not available, such as when it's in your pocket, the interaction is limited. Third, current mobiles have limited physical affordances. They only include the touch screen and few buttons on the side. Fourth, because the touch on a screen is the primary input, depending on where the user is touching, a significant portion of the screen can be blocked. And finally, the non-dominant hand is used to hold the device and is excluded from the mobile interaction. And so to solve these limitations, we introduced haptic edge display. We place it on the side of the phone so that users can interact with it without blocking the screen, and this enables the non-dominant hand to not only hold the phone, but also be involved in the mobile interaction. This is a video of the haptic edge display. It's showing a phone call application where there's a sinusoidal wave on the side to alert the user and a button on top to accept a call. With this, we can enrich the haptic interaction in different ways. First, it can serve as a haptic display. It can be used as either kinesthetic, tactile, or visual display. Second, each pins are touch sensitive and are back drivable, so you can not only tap on it, but also push. Third, with those features, it can provide dynamic physical affordances like this toggle. Finally, because of its shape-changing nature, it can be used to provide different kinds of haptic notifications. Others have also explored different ways to solve the limitations that we introduced earlier. Baudish and Chu used the back of the device as the interaction space to solve the screen occlusion problem, while Butler used the side of the phone to solve the same problem. For mobile haptics, there have been two types of haptic devices developed and researched. First is the tactile devices. These devices stimulate the user in the skin level, providing sensations such as temperature, slip, and vibration. Winfield created a display called a T-pad, in which it uses surface haptics to provide tactile sensation, which is co-located with the screen. While Pasquero created a device called Thumb on the side of the phone. It has a row of small tactile transducers to provide skin stretch deformation to the user's thumb. Second type of haptic device is kinesthetic. These devices rely on the proprioception of the user and either inhibits or guides the body movement. Hammer created a shape-changing device that uses two servo motors to either expand or tilt to provide contents like audio volume and directional information. For our device, the goal was to make a device capable of providing both kinesthetic and tactile feedback. To do so, we implemented a similar mechanism as these works. Both Summers and Follmer created a display consisting of an array of linear actuators. This enables them to create any 2.5-dimensional shapes. And for our work, we implemented a row of linear actuators instead of an array to reduce cost and size of the device. It was also in the scale between these two to provide both tactile and kinesthetic interaction. Because of its shape-changing nature, haptic edge display can be used in various contexts. When holding in hand, it can be used for haptic interaction along with the graphical interface. While in pocket, it can be used alone for haptic interaction or notification. Finally, on desk, it can be used to provide physical visual feedback. So the main feature of the haptic edge display is its display. Haptic edge display can act as a kinesthetic display by pushing on the user's finger with large displacement. In this reading application, our device varies the slope to act as a kinesthetic scroll bar. At the very top of the text, the slope is descending as the top pins are all the way out and the bottom pins are all the way in. As we scroll down, the top pins, the slope changes to ascending as the top pins are all the way in and the bottom pins are all the way out. Our device is also capable of providing tactile sensations by moving the pins with little displacement to stimulate the user's skin. Shown here is the same reading amp, but with a tactile scroll bar. Based on where you are in the text, the corresponding pin will stick out to serve as a tactile scroll bar. Haptic Edge Display can also serve as a visual display with its shape change. Here we have the phone call application in which the sinusoidal wave indicates the importance of the call. While it could function by itself, the Haptic Edge Display is designed to be usable along with a graphical interface as shown here. A heartbeat of a person is both visually and haptically communicated to the user through the screen and our device. Our device can be combined with the graphics in different ways. First, it can act as a redundant interface, where the user can choose to interact with either the screen or the Haptic Edge Display. In this radio button applications, both the Haptic Edge Display and screen indicate which button has been selected and can be used to select a new button. Second, the Haptic Edge Display can be used as a complementary interface. Here in this context application, our device is used to highlight only the favorite context through the pins on the side that move along with the screen, and they also serve as a button to enable users to more easily navigate to their favorite context by pressing on it. And finally, the Haptic Edge Display can be used to extend the contents on the screen. In this snake gaming application, pins are protruding as extensions of the snake. Our device is a bidirectional interface, meaning it can not only display contents, but also receive inputs. Each of the pins are touch sensitive, so it can be used as a button to trigger different events. In this video, group of pins are used as a button to switch between applications. They're also back drivable, so that user can not only tap, but also push on the pins. Although we don't have position sensing currently, it will be easy to implement it, and then we'll be able to detect user's force also. And so with the previous two features, Haptic Edge Display can provide various dynamic physical affordances. It can work as a toggle, radio buttons in which there are multiple states of the button to indicate which one has been selected, and shoulder buttons for natural ergonomics and gaming applications. Here, the potential of Haptic Edge Display for gaming application is shown. Buttons can be created at not only desired locations, but also at desired timings for different scenarios within the game. In addition, because Haptic Edge Display is located on the side of the phone, users can play without blocking any of the screen, unlike the current virtual buttons on the screen. With our device, we can also provide both push and pull types of notification, of haptic notifications. Push type haptic notification draws the user's attention away from what he or she has been doing to the mobile device. Traditionally, vibration motors are used to alert the user, often unpleasantly. Our device is capable of providing push haptic notification by its continuous shape change, as shown here for a phone call application. However, it can also provide pull type haptic notification. It offers a glanceable type of haptic notification where the user is given the control to decide when to be notified. When desired, user can haptically explore the static shape created by Haptic Edge Display to receive the notification. This can be useful for situations like during important meetings or presentations where the user doesn't want to be interrupted but want the choice to either glance or touch to receive the pull type haptic notifications.
So before we introduce our hardware, we would like to explain what actuators we have considered and which actuator we decided to use. We have explored 5 types of actuators. To talk about each actuator's features briefly, polymeric actuators can be fabricated on board and can protrude up to 0.4 millimeters. Microfluidic actuators will require a hydraulic actuator and valves that can control individual pins. These 2 actuators have a limit on their maximum travel, and due to this limit, they can be used for tactile interactions. SMA moves linearly because of its spring shape. Another option is to have a servo motor that has a lead screw mechanism in it. And lastly, the piezo actuator can be considered, which uses the time difference control with the friction between the vibrating rod and the mobile body. The last 3 actuators can be used for tactile and kinesthetic interaction. Taking a closer look at the table, the first 3 actuators, including polymeric actuators, microfluidic actuators, and the SMA actuators are expensive. SMA have higher power consumption as well. Servo motors using the lead screw mechanism are noisy and are not back drivable. Piezo actuators can be inexpensive when the quantity is more than 10,000, which reduces the price down to $1, but other features are reasonable for our prototype. Here, we want to explore servo motors and piezo actuators because they have low power consumption and can be used for both tactile and kinesthetic interactions. Initially, we have built a prototype that uses 24 servo motors using the lead screw mechanism, but there were several issues. This particular actuator costs about $10 each, and there is a limit on the resolution due to its large size. The speed is about 12 millimeters per second, which is pretty low to achieve fast movements, and the noise is loud. Also, it is non-backdrivable so that the buttons are not pushable. Due to these problems, we switched to the piezo actuators from servo motors. Piezo actuators are great because they're fast, quiet, and have low power consumption. Especially, their quick movement allows for them to change shape rapidly. The disadvantage is that we need to make our own control circuits and support structure. With this actuator selection, now we would like to introduce how we built the hardware. To give you the overview of the 4 essential elements, because of the constraints given by the size of actuators, we were able to use at maximum 40 piezo actuators. The device has touch sensing and communicate with a smartphone through Bluetooth. We use open loop control, which allows quick implementation without the use of sensors. You can see the device that we have prototyped. If you look at it closer, the actuators are in 2 rows, and this reduces the gap between the motors by half, consequently allowing for denser actuator configuration. With one row of pins designed, there are particular variables that needed to be determined: pin width, pitch, and travel. For our design, pin width is 1.6 millimeters, the spacing is 1 millimeter, and the maximum travel is up to 7 millimeters. In the system, we need to have a smartphone to work with the device. We have a piezo actuator, and we need a support to hold the actuators. We also have a custom PCB that we designed underneath the support, and spring pins are attached between the board and the pins, and all of them are packed into a case. So the smartphone calculates and tells you where the pin should move to, and the device tells the phone whether each pin is touched, and this is communicated via Bluetooth. Inside the device, there's a Bluetooth module, and we are using 4 microcontrollers, and each microcontroller controls 10 piezo actuators to control all of the 40 pins. 4 touch sensing modules read the touch information of 40 pins and send the information back to the master microcontroller. So as in the picture there, the mobile body consists of the moving part of the actuator and the conductive pin. The conductive pin delivers touch information through the pogo pin to the touch sensor via its spring contact. And this shows how 40 of them work in the inside of the working prototype. And application is written in Swift on iOS. We also developed an application for prototyping our device, and the movement of the actuators can be controlled visually by using this display.
So for pull-type haptic notification, our haptic edge display outputs a static shape. Then the user receives or glances at the notification by touching the shape output. And while the user could be touching the shape directly as above, it is also possible that user needs to touch it through a fabric, whether it's in your pocket or in your bag. In both cases, it is necessary to find out how well human can perceive shapes to optimize the use of haptic edge display. Thus, we ran psychophysical experiments for both in-hand and in-pocket scenarios. Since haptic edge display consists of a row of linear actuators, the only variable that we can control to adjust the resolution of the shape is travel. And more specifically, we need to find out the just noticeable difference, or JND, for travel. For our experiment, 10 healthy subjects were recruited, 8 of whom were male and were ages from 23 to 31. We used the method of constant stimuli to find the JND, and a M3L actuator with accuracy of 0.5 micrometer is used to move a single pin to a desired location. For in-hand scenario, the user directly touched the pin, whereas for in-pocket scenario, the user touched the stimuli placed inside a denim fabric. This bar graph shows the JND values and their standard deviations for travel, approximately 0.25 millimeter for in-pocket and 0.15 millimeter for in-hand. This means the users can detect static shapes with approximately 0.15 millimeter height difference when directly touching it, and 0.25 millimeter height difference for in-pocket situations. This informs app developers how they should adjust the height difference of shapes for in-pocket and in-hand scenarios. During the demo of this device in our lab and a couple of conferences, we got several qualitative feedbacks. Particularly, many users were surprised by the compelling sensation of this reading application. Even though the pins are only protruding 1 millimeter, it is still able to provide very compelling tactile sensation, and that is due to the high sensitivity of human's hand, as shown from our psychophysical experiment.
So our future plan is to improve upon our limitations and to make smaller prototypes with higher resolution. Pins can be on both sides for both hands, and lower power consumption can be achieved if we reduce the number of states. Especially to do more precise control and for more applications, the closed-loop version needs to be implemented, and we also need to consider other chips and actuators that reduce the cost. In conclusion, to improve current mobile haptic interactions, we have introduced the Haptic Edge display. Haptic Edge display enriches the mobile interaction in mainly 4 ways. It can serve as a haptic display, either with the screen or without, receive rich tactile input, provide various dynamic physical affordances, and enable both push and pull type of haptic notifications. Main limitation of this device are its power consumption, cost, and size, which we'll seek to improve in the future. We hope everyone liked our Haptic Edge display, and thank you for your attention.
So, do you have any questions for the speakers? Please come up. I have one. So, have you guys looked at?
Can you use the microphone?